So in the interests of keeping to time, I would like to call the House to order so we can begin the last of the presentations before the panel discussion. In case there are any people who've just joined us, so I'm Paul Davies and I am the moderator of this session. This is the event that you've all been waiting for. Lawrence Krauss, who is the grand architect of this entire Origins Symposium, culminating in this public day, is our next speaker. In a logical universe, we'd have done this back to front. Lawrence would have spoken first because we began with something about the human mind with Steven Pinker this morning, and we're ending with the origin of the universe. But never mind. Lawrence is a colleague and a friend of mine. He has been at Arizona State University for about a year or so, and goodness me, we have noticed a difference when he began this time last year of telling us about his plans for this Origin Symposium. I think we all felt, well, can it really be done? And the answer is not only can it be done, it has been done and done with spectacular success. So I want to begin by using this opportunity to thank Lawrence Krauss for making all this such a success. And just to give you a little taster, I don't want to intrude too much onto his time, but we've been, all of us, working pretty flat out through the weekend at the sessions, the technical specialist sessions of the symposium. And on Saturday, it began very early, like breakfast time Saturday morning. It ended at about 11 p.m. Saturday evening. And when I woke up on Sunday, there was an organizational message from Lawrence sent at 3 a.m. And he tells me that that was by no means the last message he sent before grabbing some sleep. So that is what we're dealing with. Now, Lawrence is a physicist, theoretical physicist, a cosmologist, and best-selling author. I'm not going to reel off all of his books, but he's very well known for the physics of Star Trek. And his most recent book is Hiding in the Mirror. Today, he's going to be telling us about the universe, its origin and its ultimate fate. I don't think there is a title, so I'm just going to stand aside and hand over to Lawrence. Please welcome him.
Hey, thanks, Paul. Thank you. Thank you. Thank you. I don't do podiums. Okay, this is about the time that you've been digesting lunch and nodding off, so I figured we should do a mystery story. And what I want to do is talk about a cosmic mystery story, and we'll begin. So it was a dark and stormy night. And Albert Einstein had just developed the general theory of relativity, his greatest success, his greatest discovery. Then discovered, in fact, that space and time themselves are malleable. They can bend, they can expand and contract in the presence of matter. And it was the first theory not only of how things move through the universe, but therefore, because it was a theory of space and time, it was a theory of the universe itself. And he realized, therefore, it should describe the universe we live in. But there was a problem. It didn't. The universe we lived in at the time Einstein developed the theory of general relativity was a static, eternal universe. We're talking about origins at this meeting, and in fact the conventional scientific wisdom at that time was that the universe had been around forever, more or less the same, and would be around forever, more or less the same. And in fact, it's great now living in Phoenix, because when I used to live in Cleveland, I used to have to tell people, these are stars. And now I don't have to. But, you know, when you look at the night sky, it's beautiful. And it's static, and it looks like it's not going to change much, but in fact it does. And what we've also learned is that the stuff you see is just the tip of a vast cosmic iceberg, as I'll talk about. The most important stuff in the universe is the stuff you can't see. And it not only has affected our origin, but it'll affect the ultimate future. Because in cosmology, just as in life, origins and endings are strongly tied. Now, as I say, Einstein had this picture of general relativity, but it didn't match with the universe we see. And it was quite simple. The universe we see is static and eternal. The stars hanging out there. But general relativity, just like gravity, suffers from the same problem as, in fact, as Newtonian gravity. Any of you who've taken physics know that gravity sucks. It always pulls. It never pushes. And if you put a bunch of stars out there, then the gravity will cause them to come together and eventually collapse together. And here, how could you have a universe that was fixed and eternal? Now, this was a little problem for Einstein, and he was a creative guy, so he solved the problem. Now, I'm actually going to show you how he solved the problem using Einstein's equations. So we have locked the doors, and so I want to show you Einstein's equations. Here they are. Okay, and it's not completely facetious to do this, because, in fact, in Einstein's equations, the left-hand side of the equations represents the geometry of the universe, how space itself is curved, and the right-hand side represents the stuff that makes it curved, the energy and momentum of stuff in there. And I'm a theoretical physicist, so I have to write down the Greek symbols, so there they are. I'm sure that's much more illuminating. Now, as I say, this theory of general relativity had the problem that Newtonian mechanics has, that the universe would collapse together. But Einstein realized that he could solve the problem very simply, consistent with the mathematical symmetries that had led him to be interested in the theory. In the first place, he could change the theory very slightly by adding a term to the left-hand side, which he called the cosmological term. And this term would add a small repulsive force to nature through empty space. It'd be so small that you'd never actually measure it here on Earth, but it might be able to be built up over the size of the galaxy, so that repulsive force would balance out the gravitational attraction of distant stars and galaxies, and he hoped this would solve the problem. But it didn't. In fact, it didn't solve the problem because it wasn't a problem. Within a few years of Einstein writing down the theory, it was begun to realize that the universe wasn't static after all, that our picture of the origin of the universe was drastically different. This, in fact, is I was in Switzerland a few years ago, and this is a postcard I got from Einstein to Hermann Weyl, a very famous mathematical physicist, who, some of your German is probably better than mine, but it says basically, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized if the universe wasn't static, if it was, as we now understand, expanding, you don't need a repulsive force. Because if you start the universe out expanding, gravity, which is kind of attractive, can slow it down. And you don't need this cosmological constant. And he said, for that reason and others, that it was his biggest blunder. But while word was beginning in 1923 already, in fact, beginning to circulate that perhaps the universe wasn't static, the person that convinced the world of it was someone else. And he's someone, I love to show his picture because he gives me great faith in humanity. This is Edwin Hubble. And he began life as a lawyer and became an astronomer. So there is, in fact, hope for virtually everyone. And he made many great discoveries. And in fact, one that's somewhat peripheral to what I was going to talk about is nevertheless worth mentioning. When the first big telescope on Mount Wilson was built, he discovered that there were little smudges that you used to be able to see with smaller telescopes. They call them nebulae, which is Greek for fuzzy thing. And there was a big debate about what they were, whether they were stars in our own galaxy or other galaxies, because up to that point, the only galaxy we knew of was the Milky Way galaxy, the sole galaxy in the universe. The rest of the universe was empty. Well, what he discovered with the telescope was, in fact, that those smudges were other galaxies. And we now know there are over 400 billion galaxies in the observable universe. And 80 years ago, we knew of one of them. So it gives you a sense of how this field is rapidly changing and why it's so exciting. But that's not the discovery that we remember him for. We remember him for the discovery that the universe is expanding. And what did he discover? Well, these are galaxies and not sperm. This is a galaxy, and if you look out at other galaxies, what Hubble discovered was that galaxies are on average moving away from us. And the ones that are twice as far away from us are moving away twice as fast, and the ones that are 3 times as far away moving 3 times as fast, and so on. And from this, what did he infer? Well, it's obvious what he should infer. We are the center of the universe. But as my wife, who's here somewhere, reminds me on a daily basis, that's not so. It doesn't tell us that at all. It tells us that the universe is expanding. Now, for a long time I tried to think of ways to explain this, and it's hard if we live in our universe. But if we're outside of our universe, it's really easy to see this. So I want to show you why the Hubble's law tells us the universe is expanding uniformly. We just have to look outside the box. So I make a two-dimensional universe, and here's a universe with galaxies located at regular intervals at some time t1, and the universe is a little bit bigger at some time t2. The distance between the galaxies has all gotten a little bit bigger. Now, what would you see if you were sitting on one of these galaxies, however? Well, pick a galaxy, any galaxy, take that one, and to see what you'd see, I'm just going to superimpose this image on top of that, placing that galaxy on top of itself. And what you see is precisely what Hubble saw. Every other galaxy is moving away from you. And the ones that are twice as far away from you have moved twice as fast in the same time, 3 times as far away, 3 times as fast. And it doesn't matter where you are, you see exactly the same thing. So depending upon your attitude, there either is no center of the universe or every place is the center of the universe. It doesn't matter. What it really means is the Hubble expansion tells us the universe is expanding. And that changed everything. That changed everything about our picture of cosmology and our picture of ourselves in a way. In fact, it had religious repercussions as well as everything else. It meant if things are moving further apart, they were once closer together, and that means the universe had a beginning. And we now know, in fact, that the beginning is 13.72 billion years ago, although not in Texas where I just was talking to the school board, but in any case. Anyway, so the question is, how do we know the universe is expanding? I mean, it's nice to talk about these things, but the discoveries are amazing because of the technology that we've developed to make those discoveries. And how do we know the universe is expanding? It's quite simple. There's 2 parts to it. We want to measure galaxies a certain distance away from us, and we want to measure their distance away from us, because that's how Hubble discovered that objects further away from us are moving faster. So we want to measure distance and speed. Speed is easy. To measure speed, we use the same technique that these 2 cowboys use. Here they are sitting on the plane looking at the train, and one cowboy says to the other, "I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect." And it's just really a statement that when a train whistle is coming towards you, of course, it sounds higher. Going away from you, it sounds lower as the waves get scrunched up in front of the train and stretched behind it. And for different reasons, it's true for light. The light from objects moving faster and faster away from us gets stretched to the long wavelength end of the spectrum, which is the red end of the spectrum, and therefore we call it redshifted. And so Hubble discovered that objects that were further away were further and further redshifted. But that's the easy part. How do you measure distance? We don't have tape measures that are that long. Okay? And it's very difficult to measure distance. And in fact, it's so difficult, I think I have his data here. This is the original data from 1929 for a Hubble expanding universe. So this is distance, and this is velocity. And this is one of the reasons why he was such a great scientist. He knew to draw a straight line through this data set. And not at all clear that you should do that. And in fact, when he did it, he found an expansion rate of the universe which was in fact a factor of 10 wrong. It's a factor of 10 larger than the expansion rate of the universe. And that was a noble tradition. We tried to emulate that in astrophysics ever since. And it was actually that profoundly important, because if the universe were expanding 10 times faster, it would be 10 times younger. It wouldn't be 13 billion years old. It would be 1.3 billion years old. But in fact, even then, we knew from the evidence of paleontology and geology and the things we heard about earlier in this program that the Earth is older than that. And so it was embarrassing that the Earth was older than the universe. And actually, that's one of the neat things about science, because it could have, had it been, it would have meant our picture was wrong. But of course, we discovered that Hubble was wrong, not because he wasn't a good astronomer, but because it's very difficult to measure distance. That's the hard part. To measure distance to the back of the room, I could take that projector back there and say it's a 500-watt bulb. And if I had an old-fashioned camera, in the old days you used to have light meters, I could turn out all the other lights, and I could measure the power coming to my camera, and I could know how the light spreads out, and I could work backwards to determine how far away the light bulb is. The universe isn't populated, however, by 500-watt light bulbs, which would make it easier. So we have to use something else. And we have to use something we call a standard candle. And something whose intrinsic brightness we believe we understand, and then we can look at with a telescope and ask how bright it looks and see how far away it is. And the objects we use for that are these things, the image that was in my first slide. This is a distant galaxy, far, far away, long, long ago. And this object here, this intervening object, the star, looks very bright. It looks as bright as the whole center of the galaxy. And that would make you think that it might be a star in between us and the galaxy, perhaps in our own galaxy. But it's not. It's actually on the edge of this galaxy. And it's as bright as the whole center of the galaxy because it's not a regular star. It's a star that's just exploded, a supernova, the brightest fireworks in the universe. When a star explodes, it's as bright as basically a whole galaxy. And these objects have recently become to be able to use as standard candles because we can observe them. Here's a little movie. There it is. You can see it there. It'll repeat. The star explodes in a distant galaxy. We can see its brightness. We can also measure its spectrum. And if we could measure its spectrum, the colors of light it emits, we know just what type of supernova it is. And it turns out we can determine its intrinsic brightness and use these objects to measure the distance to these distant galaxies. And we've now been able to measure Hubble's law out to much greater distances than Hubble was able to do it. It's also since the great remarkable discovery that on a log-log plot everything is a straight line. And, but when you do that, nevertheless we can measure the expansion rate of the universe now not to a factor of 10 uncertainty, but to a factor of 10% uncertainty. So things have moved remarkably well in the last 80 years. This was really the major purpose of the Hubble Space Telescope initially, which is why it's called the Hubble Space Telescope, to measure that expansion rate. Now, let's go back to Einstein. Einstein said it was his biggest blunder, the cosmological constant, so he wanted to get rid of it. But it's kind of like trying to put the toothpaste back in the tube. If Einstein hadn't introduced the cosmological constant, someone else would have. Because using the miracle of modern mathematics, we can rewrite this equation. And I mean, this is not very difficult mathematics, but it's a small step for a mathematician, but a giant leap for a physicist. Because not just to move this from there to there, but remember, when you put this term here, it has a very different meaning. The stuff here had to do with the geometry of the universe. The stuff here has to do with the energy and momentum in the universe. So when I put it there, it means that if it was there, it would represent a new form of energy in the universe, some as of yet undiscovered type of energy. We can ask, what type of stuff would have that type of energy? And it turns out there's only one type of stuff: nothing. Now, by nothing, I don't mean nothing. I mean nothing. I mean, if you take space and get rid of all the radiation and all the particles and everything, you have nothing there. If space weighs something, then that's the kind of energy you'd have. Now, if you ask a 4-year-old, what's the energy of empty space? The 4-year-old would say nothing, okay? Because that's a reasonable, if there's nothing there, it shouldn't have any energy. But the 4-year-old hasn't taken quantum mechanics, however. And it turns out that in the quantum mechanical universe, empty space isn't so empty. It's a boiling, bubbling brew of virtual particles popping in and out of existence so fast that you can't see them. And it sounds like, you know, counting angels on the head of a pin. If you can't see them, how do you know these virtual particles are there? And the answer is, well, you can't see them directly, but you can see the effects indirectly. The fact that they pop in and out of existence changes the properties of matter. In fact, we can use it to calculate very carefully the properties of atoms, and we come up with incredible accuracy. Most recently, we can use it to calculate the properties of protons and neutrons in atoms. This is a picture of what the space inside of a proton looks like. It was a picture that was shown at the Nobel Prize ceremonies, in fact, by 2 of the people who are going to be on the stage next, who won the Nobel Prize for, in fact, explaining what the space inside of an atom, of a proton, looks like. But it's a boiling, bubbling brew of stuff. It's responsible for most of the mass of your body, in fact. So we can use these principles to, in fact, calculate properties of elementary particles. And now, if empty space isn't so empty, we should be able to use the same ideas to calculate the energy of empty space. And when we do that, we come up with an answer. And it is that the energy of empty space should be roughly a gazillion times the energy of everything we see. It is the worst prediction in all of physics. Now, and I firmly believe that, because in fact it turns out to be 120 orders of magnitude larger than would be allowed just if it was any larger than the energy of matter in the universe that we now have. If it was a lot greater, we wouldn't even be here. And so this is really the worst prediction in all of physics. So that's been around since I was a graduate student. And we had a simple solution. It was like that cartoon where people are drawing on the blackboard and there's a little gap that says, and then a miracle occurred. And the point is, we knew what the answer was. The answer was the energy of empty space had to be 0, because that's the only sensible value. And the reason we knew it had to be 0 is that there's no way you could imagine, say, canceling this huge number to 120 decimal places, leaving a 1 in the 121st decimal place. It's just impossible to imagine any mechanism to do that. But you could imagine a mechanism to make it precisely 0. 0 is a beautiful number. And symmetries of nature can cause positive and negative things to cancel exactly. So we figured there's just some new symmetry of nature, and we could sleep at night knowing, indeed, the energy of empty space was 0. But the nice thing about cosmology in the last 20 years, at least, is that it's become a science. And science requires empirical evidence. And so instead of saying we know it's 0, the question is it? Can we measure it? And to do that, we very simply have to weigh the universe. And that may sound daunting, but it's something that's been going on for a long time. We do it because we can stand on the shoulders of giants. Here's one of the early giants, or sort of. This is, I took this in a picture on an island off Sweden called Ven. This is a very famous astronomer named Tycho Brahe. If you look carefully, you can't see the end of his nose there. Got cut off in a sword duel. But Brahe and others led, in fact, his observations of the motions of planets around our solar system led, in fact, his assistant Kepler to develop laws of motion, which led to Newton to develop his universal theory of gravity. And gravity has allowed us to weigh things. It's a long story, and a story I don't have time to adequately tell, but we can actually now use gravity to weigh the universe, to try and come up with what the universe looks like. And we care for the following reason. In general relativity, matter curves space. And one of the big questions of 20th century physics was, is there enough matter to curve space back on itself, to produce a closed universe? In a closed universe, if you look far enough in that direction, you'll see the back of your head. Okay? And we could live in one of 3 universes. A closed universe, these are 2-dimensional universes, they're a lot easier to draw. Our universe is 3-dimensional. But our universe could be open, closed, or the exact boundary between the two called a flat universe. And that sounds very nice, but what it really meant, we thought, was in a closed universe, there's enough gravity, enough mass to stop the expansion of the universe and cause it to recollapse. In a big crunch, the reverse of a Big Bang. An open universe will go on expanding forever, and a flat universe will just slowly grind to a halt but never quite stop. And the big question was, which universe will we live in? Because when we know that, we know our future. In fact, that's why I got into cosmology. As an elementary particle physicist, I wanted to be the first one to know how the universe would end. And it seemed like a good idea. So I wanted to know what makes up the universe and how to weigh it. And this long saga, in fact, has reached a result in the last few years. We're now almost up to the present time. Only within the last 10 years or so have we really been able to weigh the universe. And I want to show you the 2 ways we can. This is one way. This is a remarkable picture. Every object in this picture, it's from a Hubble Space Telescope, every object in this picture is a galaxy, not a star. Every one of these galaxies contains hundreds of billions of stars with planets around them, maybe apropos of the last few talks, maybe with civilizations around them. We don't know. But every single one of them is a galaxy. And galaxies like to hang around in clusters. We're in a cluster. Most galaxies are clustered together. And clusters are the biggest bound objects in the universe. Anything that can fall into anything will fall into a cluster. So if we can weigh clusters, we can get a sense of the total mass of the universe. And we can weigh this using this picture. You'll notice, you don't have to be a rocket scientist to notice there's these weird blue things in this picture. And what this is a phenomenon that Einstein first proposed could have happened in 1937, although he said observers will never measure it. And that's because he underestimated observers, which is often easy to do. Because Einstein had told us that if you have a big mass, it will curve space around it. And therefore, it can act like a lens. Just like the lens in my glasses bends light, focuses it in so I can see. If I had a magnifying glass and bend the light, you'd all be bigger. If I had a goblet, a cut glass goblet, and I looked through it, I'd see many, many versions of you. And space can do the same thing. This is a large enough mass distribution that what we are seeing are multiple images of a single galaxy located several billion light years behind this cluster. All of these images are of the same galaxy, stretched and distorted, and it's a beautiful picture. But we can use it to weigh the galaxy, because we can say, we know how general relativity works. What mass distribution would produce that image? And Tony Tyson and collaborators have inverted that image, and here's a picture of where the mass is. These are the spikes where galaxies are, but you notice that most of the mass in that image is between the galaxies, the stuff that isn't shining. The empty space apparently between the galaxies accounts for about 50 times as much mass as the galaxies themselves. There's something in that system, and physicists, with their incredible linguistic perspicacity, have called it dark matter, because we can't see it. And we've now established definitively that not only our galaxy, but every galaxy in the universe is dominated by this dark stuff, and we think it's a new type of elementary particle. What makes that even more exciting is, if it's an elementary particle, that dark matter isn't out there just there. It's in this room. It's going right through your bodies as you nod off during this lecture. Okay? And that means we can actually build experiments to look for it underground. It also means we might actually produce it in our accelerators. We are at a point where it's quite likely, many of us think in the next decade, if not sooner, we might actually be able to directly detect this stuff. And I don't know if I have a picture of a dark matter detector. No, I may, but I don't want to talk about it right now. The point is, by weighing this cluster and other clusters, we have now been able to weigh all the mass in the universe and to ask whether the universe is open, closed, or flat. Now, there's a Greek letter down there. Whenever something's important in physics, we give it a Greek letter. And omega is the ratio of the total amount of matter in all the clusters in the universe divided by the amount of matter you needed to make the universe closed, just closed. So, or the exact boundary is flat. So omega equal 1 is a flat universe. Omega greater than 1 is a closed universe, and omega less than 1 is an open universe. So now we have finally, after 80 years of trying, definitively been able to determine that there's not enough matter by a factor of 3 to make the universe flat. So the universe appears to be open and it'll expand forever. There's a problem with this observation, however, and that is that theorists didn't believe it. Maybe it's a problem for theorists, but the point is, just like 0 is a pretty number, there's another pretty number, and it's 1. We believed, on the basis of all of our theoretical biases at the time, based from arguments from elementary particle physics, that the only sensible universe is a flat universe. And the reason is quite simple, and maybe we can get to this in the question period. Only a flat universe can result from nothing, because the total energy of a flat universe turns out to be precisely 0. And so we believed the universe had to be flat because we thought the universe came from nothing. But here these pesky astronomers were coming up with the wrong answer. Well, the point is, this is a very indirect way to measure the geometry of the universe. After all, it's using Einstein's equations. You measure the mass of the universe, and then you got to use Einstein's equations to turn it into geometry. It's crazy. Let's measure the geometry of the universe directly. Oh, well, this is an experiment to detect it, but I want to go to the geometry of the universe. So how would you measure the geometry of the universe? Well, let's ask the question, how could you measure that the Earth is curved if you couldn't go into a satellite and look at it, and you couldn't go around it? Okay. Well, very simply, you draw a triangle, and then you'd ask a European high school student what's the sum of the angles in a triangle, and they'd say 180 degrees, and then you'd say, well, that's fine, but except you learned your geometry from Euclid. On a curved surface, something very different is possible. Here's the Earth. I can draw a triangle that's quite different. I can draw a triangle. I go along the equator. I make a right angle up to the North Pole. I make a right angle, come back down. And I have a triangle with 3 right angles. 3 times 90 is 270. So if I have a big enough triangle, I can know the Earth is curved. In fact, interestingly enough, the first mathematicians to think about curved geometries actually tried to measure big triangles on the Earth to see if, in fact, not the Earth was curved, but if three-dimensional space was curved. Because it turns out this is true not just for a 2-dimensional surface, but for 3-dimensional space. If we could find a big enough triangle and measure it, we would determine whether the universe is open or closed or flat. And in the last 10 years, we've been able to find a big enough triangle from the most important and remarkable measure in cosmology, and that is the cosmic microwave background radiation, the afterglow of the Big Bang. In fact, one of the other Nobel laureates who's going to be on the panel here won a Nobel Prize for actually looking at this stuff and helping discover one of the things I'm going to talk about. What is the cosmic microwave background? Well, as I say, it's the afterglow of the Big Bang. Now think about it. When we look out at objects that are further and further away from us, we're looking back in time. Objects that are a billion light years away from us, we're looking at them as they looked a billion years ago, 2 billion years ago. So if the universe is 13.7 billion years old, if we look out far enough, we should see the Big Bang. But we can't. We can't because there's a wall between us and the Big Bang. Not a physical wall, but a metaphorical one, perhaps. I can't see outside this room because, as you can see from my laser there, the walls are opaque. As I look back in the history of the universe, earlier and earlier times, the universe was getting hotter and hotter and hotter. And at a time when the universe was about 100,000 years old, it was a temperature of about 3,000 degrees of absolute zero. And at that temperature, something very special happens. Most of the universe is made of hydrogen. Most of the normal matter in the universe, I should say, is made of hydrogen. And at that temperature, the radiation is hot enough to break up our hydrogen into protons and electrons, charged objects. So instead of having neutral matter, you have a charged plasma. And a plasma is opaque to radiation. And so we can't see past this surface, literally. That's the bad news. The good news, however, is if we run the film forward as the universe is cooling down, and eventually at a certain point, the universe cooled down so the hydrogen could combine together into neutral matter, and neutral matter is transparent to radiation. So we should be, just as I can see the wall when the lights are on because the light is absorbed at its surface and re-emitted, and the air between me and the wall is transparent, if I look out, I should see radiation coming at me in all directions from the Big Bang. And that was precisely the radiation that was discovered by accident in New Jersey, of all places, in 1965 by two people who didn't know what on earth they were doing or why they were doing it, perhaps, but they won the Nobel Prize anyway. Now, they won it because it gives us a picture of what it gives us definitive evidence that there was a Big Bang, and yes, there was a Big Bang. But also, more importantly, it gives us a picture of the universe at early times. If we can image that background, we could see what the universe looked like. And I'll show you a picture in a moment. But on that picture, there's one important scale, 1 degree across. Why 1 degree? Because the universe is 100,000 years old, and this distance represents 100,000 light years. Now, Einstein tells us that no signal can travel faster than the speed of light. And that means this represents a very important scale. Because if I have a lump of matter smaller than that scale, it will collapse due to gravity. And as it collapses, it'll heat up and pressure will respond and all sorts of stuff will happen. But if I have a lump that's this big across, it doesn't even know it's a lump. It's like Wile E. Coyote when he goes off the cliff, okay? Gravity can't transport across it. It's just too big. So it won't start to collapse. So the largest lumps that will have significantly collapsed at that point are this big, are 100,000 light years across. That gives us a ruler. Because we have a 100,000 light year across ruler, a known distance away from us, and in a flat universe, light rays travel in straight lines. And the angle subtended on my eye by a 100,000 light year across ruler at that distance will be 1 degree. However, if the universe is open, then light rays will diverge as you go back in time, and the ruler will look smaller, maybe ½ a degree. And if it's closed, light rays will converge, and the ruler will look bigger, maybe 2 degrees. So we just have to image that picture, and we can look for the lumps and ask how big are they? Are they 1 degree, ½ a degree, or 2 degrees? And we can measure the geometry of the universe. And that's precisely what's been done recently. This was one of the first experiments to do it. It's called the boomerang experiment. It was in Antarctica. A big balloon took a microwave radiometer up way above the Earth's atmosphere, or at the top of the atmosphere at least, and it went around the world, which is actually easy to do in Antarctica. But in this case, it took about 2 weeks to do it, and it imaged a small region of the microwave sky looking for hot spots and cold spots in the radiation, which correspond to lumps of matter and energy. And this is actually the picture it took, a false color image of the picture. It reminds me of our cosmic myopia. in fact, because here's the hot spots and cold spots in the microwave background superimposed in the original image. And the point is, we don't see microwaves, which is what this radiation is. We see visible light. But if we evolved to see microwaves for any reason, instead of having evolved to see visible light, every night when you looked out, more or less, you'd look out and see the microwave background 13 billion light years away. Now, there are the lumps. How big are they? Well, we can create universes on a computer. Here's another false color image from the boomerang map. And here's a closed universe built on the computer, an open universe, and a flat universe. And you see in the closed universe, the lumps are bigger than these lumps. In an open universe, the lumps are smaller than these lumps. But just like Goldilocks, in a flat universe, the lumps are just right. In fact, so just right that I can blind you with, well, actually, we've even done a better job, and I put this up in honor of the physicist David Wilkinson, who, if he were still alive, would be here with us today, I'm sure. And the Wilkinson microwave anisotropy probe actually took a picture of the entire microwave sky and allowed us to do a better job. And just to show you, this is an image which shows what you would expect. The curve is where you'd expect most of the lumps to be, about 1 degree across, if we lived in a flat universe, and this is the data point. We now know with great precision, about 1% to 2% precision, that we live in a flat universe, just like we thought, the theorists. But there's a problem. I hope those of you who've been awake realize that we just proved the universe wasn't flat. We added up the amount of matter in the universe, and found out it wasn't flat. So what's the problem? If the universe is flat, we're missing 70% of the energy of the universe. Where could it be? Well, maybe it could be in the energy of empty space. Stupid, crazy, nonsensical. But if it were in the energy of empty space, what would happen? Well, if I put energy in empty space, I remind you, it acts like a cosmological constant, it's gravitationally repulsive, and it would cause the expansion of the universe to speed up, not slow down. And in 1998, observers who were trying to measure the deceleration of the universe, how fast it was slowing down, discovered something that amazed me. This may not seem like it's much, but it was on the cover of Science, in fact. This is the Hubble expansion that I showed you earlier, and the question is, does it curve up or down? So let's draw a straight line through it. And this curve here is exactly what was predicted for a universe that should slow down, a flat universe that should slow down. And you see, it doesn't match the data at all. The data is above, on average, the straight line. And if I try and fit the data, I fit to an accelerating universe. And the amount of energy I need in empty space to fit that acceleration is exactly the amount that was missing. 70% of the energy needed to make the universe flat. So we now have a consistent, unbelievable picture of the universe. A cockamamie, crazy, insane universe. When I want to remind you of this as we think of our origins. Okay? We now know that you take all the stars and galaxies and everything you see, that accounts for less than 1% or so of the mass of the universe. You are cosmically insignificant. We can get rid of you and all the aliens and all the stars and all the galaxies, and the universe would be largely the same. It would be a sea of dark matter, 30% dark matter, and 70% dark energy. Okay? So much for a universe designed around us. But having a universe in which nothing is the dominant stuff is certainly something that's put physics on its head. Because we have no idea why it's there. In particular, if anyone tells you they understand that, you should not believe them, especially in this case if they're a string theorist. But in any case, since Brian has left, I can say that. But what really makes it exciting is that its existence is probably tied to the very beginning of time. To understand it may mean we may understand the origin of the universe. And what's also important, and in the last 2 or 3 minutes of the talk, is it will determine our future. Our future is very different than we thought it would be. And this will bring up a few interesting things to talk about, perhaps, maybe, if we have time. This is a brief history of time. This is the history of the universe, where this is the density of matter as the universe is expanding, the density falls off. But this is the energy of empty space, which remains constant. What time are we living in? Right here. Now, there's something weird about that picture. Why are we living in the only time in the history of the universe when those two curves cross, essentially? 14 billion years after the Big Bang or so. It's just a random time. Why should we be living at the only time in the history of the universe when those two curves are the same? Well, people have suggested an answer to that, and that's that galaxies exist. Because let's say the energy of empty space were 50 times greater, so it wasn't down here, it was up here. Well, then these two curves would cross here. Not now, but at the time galaxies first formed, about 12 billion years ago. But if the energy of empty space dominated at that time, it's repulsive. And galaxies would therefore never have formed, because the repulsive force would have beaten out the attractive force, and there'd be no galaxies. So some physicists have argued the reason the energy of empty space is what it is as follows. If there are many different universes, and the energy of empty space can vary in each one, then only in those in which it's not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure it. That may seem like nonsense to you, and to many physicists it seems like nonsense. And we had an interesting discussion and debate about that idea at our meeting, and I recommend you watch it when we archive it on the web. But it's a fascinating possibility. The question really comes down to something Einstein asked. He said, what really interests me is whether God, and by God he meant something other than God, but what really interests me is whether God had any choice in the creation of the universe. And what he meant by that is there only one consistent set of laws of physics that can happen to make a consistent universe, or are there many different kinds? And really the history of physics over the last 400 years has been to demonstrate that apparently there's order to nature. There is a consistent set of laws. And this is a subject that's now being debated very highly, because we don't know if our universe is an accident and we're in it just because we can live in it, a kind of cosmic evolution. It's nothing to do with design. It's really cosmic evolution. Why is our universe fine-tuned for life? Apparently the same reason that a bee is fine-tuned to be able to find honey, because if it didn't, it wouldn't be around. So, in the last minute, what does it imply for the future? Well, this is a commencement address. I've given two of them. And I never had the guts to use this line, which was at a private girls' school, where the man said, things are going to get unimaginably worse, and they're never, ever going to get better again. But that's apparently the way it is with the universe. Because, in fact, the future of the universe poetically takes us back to our beginnings, at least in the 19th century. As the universe, if dark energy persists, then the universe will speed up. And it will carry away all the galaxies we now see until they are in fact moving away from us faster than the speed of light. And they will disappear. And in the far, far futures, observers that look out will only see a single galaxy or metagalaxy as our local cluster collides and produces one large galaxy. And they will come up with a picture of the universe which is completely wrong. A picture in which there's a single isolated galaxy surrounded by empty space without any evidence of a Big Bang at all. A picture we now know to be wrong, the one we had in 1900, and that we've learned in the last 100 years is completely different. And I find that poetry appropriate because art and science are strongly connected. Einstein himself said that the fairest thing we can experience is the mysterious. It's the fundamental emotion that stands at the cradle of true art and true science. And so you may be depressed. You should be, perhaps. Because let me summarize. You are cosmically insignificant, and the future is miserable. But you shouldn't really be, because science has produced this incredible picture, this picture that is much more interesting than any fairy tale or fable. And we produce objects and technology that allow us to take pictures like this. This is not a painting. This is a NASA picture, the Cassini satellite, of Saturn, of an eclipse of the sun by Saturn. But what's really neat, and you can't see it due to the resolution of this screen, but go to the NASA website, and right here, you'll see a pale blue dot. Right between the rings, if you look in the distance, you'll see the Earth. That's shining as a pale blue dot. And so, even though we are cosmically insignificant, we should really enjoy our brief moment in the sun when we are lucky enough to have evolved the facilities to be able to explore the universe back to its earliest moments and its far future. That's what science is all about. Thank you very much. Okay. Do we have any time or not? Maybe 2 minutes? We have time for 1 or 2 questions. Yeah, we can go a little bit late. 2 minutes.
Well, that's a wonderfully upbeat note to end an otherwise downbeat lecture on. We don't have a great deal of time for questions, but when the universe as a whole is the subject, there normally are 1 or 2. And so I'm going to moderate that, and we'll start on the left-hand side over here.
Yes, Dr. Krauss. My name is Jim McWhorter. We spoke last Friday.
Yes.
In 1920, around that time, somebody said that the galaxies were moving away from each other like dots on an expanding balloon.
Uh-huh.
Over the years, that explanation has gone from dots on the surface of an expanding balloon to dots within a very, very thick membrane of an expanding balloon, and all starting from the Big Bang singularity and moving outward along radial lines. The problem I have is that there's no connection between the behavior along the direction of the radius and the circumferential rates.
Yeah, I know. That's okay. I know where you're heading. That's why I didn't use the expanding balloon. It's a picture that gives you a sense of, because people say, well, how can everything be moving apart if it's not moving into anything? And when you have the picture of an expanding balloon, you're not supposed to think of the space. The surface of the balloon is all there is. It's a two-dimensional universe. And on that two-dimensional universe, nothing exists inside or outside of the balloon.
But
Let me finish. I'm up here. So on that surface, I could put dots, and when I blow up that balloon, it expands. But the balloon is not the surface of that balloon is not expanding into anything. It's just getting further apart. But many people are confused by the fact that, in fact, we live in a three-dimensional space, and they think of what's inside and what's outside the balloon. That's why I didn't use that picture. That's why I used the explanation I did, which is a completely flat plane. And in that case, it seems to me it's a lot easier to understand than expanding universe. An expanding universe like ours, if you want to take the two-dimensional analogy, a better analogy is think of an infinitely big bed sheet. It was infinitely big at the beginning, it's infinitely big now, but I'm stretching it.
Okay, there is a three-dimensional model that'll explain the expansion of the universe without the necessity of a Big
I am
Bang.
the moderator.
Yeah, there are many. Okay, I'm sure you'll write me about it, but I don't think we should talk about it here.
In the interests of fairness, because we have somebody waiting on this side, and we are very limited in time. So, go ahead. Sir.
You mentioned string theory and its proposed reasoning for the dark matter and dark energy we see in the universe. In your opinion, with the lack of experimental evidence, is it a kind of deus ex, wishful thinking from scientists? Is it, to quote Fermi, not even wrong?
No, I think it was Pauli who said that. But in any case, no, if it was, I really wouldn't talk about it. I don't believe in talking about things that are so speculative that they shouldn't see the light of day, at least in public. No, in fact, I don't know if he's out here, but you'll hear him in a minute. My friend Frank Wilczek likes to coin the term radically conservative. The idea of dark matter, in fact, is the most conservative possible assumption. It's the simplest thing that explains everything we see. Moreover, it's fully expected. That's the other thing I should have pointed out. Every idea in particle physics, not string theory, because it actually doesn't go as far as to make any kind of predictions, but any of the tentative ideas we have in particle physics of what we might see at the Large Hadron Collider, all of them suggest easily a new type of particle which could be dark matter. I think of the following. Maybe this is the way to end. We did not know of the microwave background until 1965. What's the microwave background made of? Light. The most visible stuff in the universe. And it turns out that there are 1 billion particles of light in the universe for every proton in the universe. There are 1 billion times more, in terms of number, particles of photons than protons. Now, it turns out photons are light. They're massless, in fact. They still have energy, and their energy doesn't compare, it turns out, with the energy of matter. But it wouldn't be very hard in the early universe to make some other kind of particle which is heavy, which is a lot more abundant than protons and a lot easier to see, a lot harder to see than light, and it would be the perfect dark matter. And that's exactly what we're doing. We're looking for those type of particles in the detectors, this picture I showed here, and hopefully we might produce them in the Large Hadron Collider. And that's what makes us so excited right now, because we're on the threshold of potentially turning what you might think of as myth into science. Thank you. Thank you. Well, five, yeah, there's a break. Well, yeah, if you say there's a break, then you might as well, because I'll come back.
Well, that's a great way to segue into our next presentation or event. There's a 5-minute only break now, following which we will have a panel discussion. We have to rearrange the stage here. So if you need to step out, please do so quickly and be back in no later than 5 minutes.
except I can't. Katie?
Here he comes. Oops,
It's all right.
there's names there.
What?
The-
It's all right. It's
Okay.
okay. Okay. We are, I'm very pleased and privileged to introduce a friend of mine, and Ira Flato. This is his 40th year as a science journalist, and certainly one of the best science journalists in the country for any of you who listen to Science Friday. And yes, let's give him a round of applause. But if hurting scientists is like hurting cats, hurting Nobel laureates is, I don't know it's worse. And there are very few people I would trust with the incredible challenge to do that. But I know that this next panel, not only from the constituents of the panel, but the moderator, will be absolutely enthralling. So I'm very pleased and privileged to call out Ira Flato.
Thank you. Thank you. Thank you. I just wanted to say that filling up this theater, if you're looking for Frost Nixon, they're out of town by now, but filling up this theater with people who come to watch and talk about science is a testament to you folks more than to the folks up here on the stage. You deserve a round of applause for yourselves for coming out and showing how popular science is for the people who don't believe that science has a rightful place in our society. So thank you all for showing up today. And as a reward, we have two things. We have 6 Nobel Prize winners. You've heard Lawrence all afternoon talking about you're going to see the Nobel Prize winners come out this afternoon. And they're out there. I know, don't get too close, right? And also, everybody's got these pent-up questions they want to ask, so we're going to take a lot of questions that remain unanswered. People were standing in lines. So get on those lines a little bit early, because what happens is no one gets in line, then everybody gets in line, and then you never get to ask your question. So we're going to try to follow up on the topics we talked about today. Things you've heard about, talk about some of the details. We're going to talk about cosmology, and we're going to talk about astrobiology, the search for life in our solar system and in the universe, with our eclectic panel of scientists. And let me introduce them to you now. Let's see if they're all in the seats. Okay, we'll start here. Close to me is Burt Blumberg. He is Distinguished Scientist at Fox Chase Cancer Center in Philadelphia, and the University Professor of Medicine and Anthropology at the University of Pennsylvania. And his research has covered many, many areas. He was awarded the Nobel Prize in 1976 for, quote, discoveries concerning new mechanisms for the origin and dissemination of infectious diseases, and specifically for the discovery of the hepatitis B virus. And we have a vaccine for that now because of his discovery. He's also now involved in astrobiology. Burt Blumberg. Next to Dr. Blumberg is David Krauss. He's been director of the Institute of Theoretical Physics at the University of California, Santa Barbara since 1997. In 2002, he was named the Frederick Gluck Chair in Theoretical Physics and the director of the Kavli Institute for Theoretical Physics. And in 2004, he and Frank Wilczek, who's sitting on the other table over there, these are the particle physics people that Lawrence was telling you about, and David Pulitzer were given the Nobel Prize in Physics for the discovery of asymptotic freedom and the theory of a strong interaction. Thank you, David, for showing up here today. Next to him is Dr. Sheldon Glashow. He is the Arthur G.B. Metcalf Professor of Sciences at Boston University, and in 1979, he shared the Nobel Prize in Physics for his contributions toward the unified theory of weak and electromagnetic forces. He'll talk about that. On the moving to the second table is Walter Gilbert. Dr. Gilbert worked on the mechanisms of protein synthesis And it's a mouthful, so I'm not going to get into the whole thing. Let's suffice it to say he is co-founder of Biogen, Myriad Genetics, Paratech Pharmaceuticals. He's now a venture capitalist, and he received the Nobel Prize, the 1980 Nobel Prize in Chemistry for rapid DNA sequencing, and he's now currently as a photographic artist, right?
Correct.
Welcome, Dr. Gilbert. Next to Dr. Gilbert is John Mather. He is senior astrophysicist in the Observational Cosmology Laboratory, and that's at NASA's Goddard Space Flight Center. That is actually the oldest center of NASA, is it not? Yes. And he came to Goddard to be the principal investigator for all this cosmic background radiation stuff that you have seen, that Lawrence has been showing you, other scientists have been showing you. And he is a recipient of the Nobel Prize in Physics in 2006 with George Smoot for this kind of work that he's been doing. Welcome, Dr. Mather. Last but not least, at the end is Dr. Frank Wilczek, and he has received many prizes for his work in physics, including the Nobel Prize of 2004 for work he did as a graduate student at Princeton when he was only 21 years old. So it shows you that you can do work early on in your life and get credit for that. He's known, among other things, for the development of quantum chromodynamics, the invention of axions. Were they named after a laundry detergent?
Yes.
It was.
Yes.
Particle named after a laundry detergent. And we might get into how we name new particles. That's kind of an interesting subject. And the exploration of new kinds of quantum statistics called the anyons. So welcome to Frank Wilczek. Let me begin by talking about a topic that was peripherally talked about today, but we have not gotten into. We've talked about the size and shape of the universe and how life may have started, but let's say we all have accepted those ideas. Now, where do we go to look for life in our let's limit to our own galaxy for now, and we'll branch out to other galaxies into the universe. Dr. Blumberg, where is a good spot? You work for NASA thinking about these things. Where should we be going to look for? Where's the best candidate in our solar system?
Well, keep in mind that the definition of astrobiology that's often used is the study of the origin of life. We know life's around. The question is, how did it start? And then testing the hypothesis that life exists elsewhere. So the question is, what seem to be the best candidates within our solar system for the existence of life? Well, the primary candidate has been Mars. Mars is the planet that, at least in early days, was most similar to Earth, and perhaps a good part of its early history. There are many similarities. It's changed a great deal. There's one of the requirements for having life is to have liquid water, stuff that chemicals can dissolve in. And there's geological evidence on Mars that there were great outflows of water, perhaps sporadically in the past. There's very little evidence of recent flows of water, although there may be some. And it has an atmosphere, not a very healthy one, quite toxic. And water ice has been discovered in several ways, spectrophotometrically and with actually in effect sort of seeing it. So that is the primary candidate. A secondary, a very important candidate is Europa. Europa is a moon of Jupiter's, as I'm sure most of you know, and based on observations and certain measurements and theoretical considerations and some very close observations, it appears that the upper many kilometers, 10 or more kilometers, are made of water ice, and there appears to be a briny ocean under this thick layer of ice. Now, and then there's a solid core. So one of the requirements for life, as I said, is water, and I think the estimates are there may be